So we know how to do it by hand. It's very time consuming, but it can be done. Essentially, the formula that we use for the difference between two population means is subtract the means of the sample, plus or minus some multiplier, as it's called, and you do the standard error. And the standard error, if you wanted to do it by hand, is given by that formula. And that's kind of where we were. And you can get a 90, 95, 99. The guy here called the multiplier. It depends on two things. It depends on the confidence interval that you want. So you might want a 95%, for instance, but you might want a 99. And it also depends on the size of your data. And that boils down to a guy called degrees of freedom. In a lot of ways, figuring out who the degrees of freedom are is quite messy. And that's because it really depends on circumstances, how it's calculated. The simplest way to do it is you combine the data and then you take away one. So if you had 40 numbers in your first set and 50 numbers in your second, that adds up to 90. And so your degrees of freedom, in that case I just mentioned, the degrees of freedom would have been 89. But that's not the only way of doing it. You could, for instance, and I have seen this, where the degrees of freedom are actually, you add the two together and you subtract 2. So that would be 88. So that one would be add them together and subtract 1 for each. I've seen that before. And there is a third way you can do it. And the third way is that the degrees of freedom, it's the smaller of the two answers. What do I mean by that? It's a smaller one of that guy or that guy. So in this case, that would be 39 and this one would be 49. And so the degrees of freedom in this case up here would actually be 39. And there is yet another way to calculate degrees of freedom, and that's using a horrible formula, which I've mentioned a few times before, where I am not going to show you because there's no point in us ever even thinking about that. The good news is that since we're going to use the software, we'll let the software figure out how it's going to calculate the degrees of freedom. So you're going to look at a question where if you just add the two data sets together, and you might think that the degrees of freedom are 89 or 88 or even 39, and you find out that the answer is 47.12, and you wonder where that came from. That's because it probably used a weird formula that I'm not writing down over here. So don't be concerned about why are the degrees of freedom not what I think they should be. Just assume that WebAssign knows what it's doing. I've done a couple of examples and I can't actually figure out where the degrees of freedom are coming from. I'm assuming that it's that weird number, but who knows how it's been programmed. So let's just pick a couple of examples and call it good. Right. So first one I'm going to look at here, and I've got the answers as well, but that's fine. Is question 7. I wonder if I can make that a little bit bigger without cutting off any of the words. Is it 7 or 8? Which one am I doing? I'm doing 8. Okay, here we go. So we're going to do the cold one because they have no imagination. And that's the one where you caught a cold and there were 2 groups. One of the groups who caught the cold just got a placebo. The other got a zinc lozenge. And they figured out how long it took their colds to go away. And the data is in here. So hopefully when I hit use salt, you can see it. I'm going to go to inferential statistics and make it a 2-sample T. Okay, so I'll have to get the numbers. Oh, what'd you do that for? Okay, technical issue. My question disappeared when I hit that, and I went, oh, has it disappeared or is it just hiding? It's hiding. Okay. I'll have to write these numbers down, then I will return to the question. So what do we know? 21 of them took the zinc. That's here. 29 of them took the placebo. Okay, we got that. Right, so the group, God, this is hard for my brain to read. Suppose it's like a lawyer got these questions. Suppose that in truth, everyone in the population took symptoms would last on average 4.5 days. So that is the mean of people who took and a standard deviation of 1.5. Okay. While those who took the placebo, the average would be 7 days and the standard deviation would be 3. Okay. Right, I'll return back to the whiteboard for a second just to show you all the stuff that I've written down. And here we go. If you took the zinc, there were 21 people in that group. The cold lasted on average 4.5 days and the standard deviation was 1.5. If you got the placebo, there were 29 in that group. The average length of the cold was 7 days and the standard deviation was 3. And we're being asked to calculate in this order. So it's placebo, take away zinc. And of course, that means that these are all 1s because they're the number that you start with. And these are all going to be 2s. Okay, now I've got the data. I'll go back and we'll let salt do everything else. So here we go. Inferential statistics, 2 sample. Sample 1 is the placebo people, so I'm going to put in the mean, and the mean for them was 7. Standard deviation for the people who got the placebo was 3, and the sample size for this particular group was 29. If you move on to the second group, that's the ones who actually did get the zinc. Their cold only lasted 4.5 days. The standard deviation for that group was a lot smaller, 1.5, and the sample size for that group was 21. Going to go down and click on confidence interval, and they want eventually they were looking for it. Well, it's probably coming later. Let me scroll. No, they don't even want a confidence interval, go figure. Well, we'll do a confidence interval anyway. That's just extra work. I'm having a lot of technical difficulties today. I've lost my thing. I've lost my window. Where the heck are you? Anybody know how you get a window that's so small you can't see it?
You can try pushing Alt-Tab, and then that'll switch to like a different window.
Let's see if I can find it. Otherwise, I'm going to have to. Okay, I've got a whole list of windows. And there it is there. Why can't I see it? Okay, let's forget about this and pretend I start again. I click on it. Oh, God, Himmel. I am such a nice person. I'd be cursing right now. Okay, let's go even further back. I'm going to close every window in sight, and that way the little baby window, wherever it is, there it is there. Why can't I get you? Okay, I'll close it. This is the time where I should go and have a coffee, because it'll take me half an hour to make this damn thing work. Right. I don't know how many times this is. This is the third time lucky. Some weird number like that. There we go. And we got our window back. Can you, oh, you can't, I don't know what you can say. You are not seeing the grief that I was going through, perhaps. There. Can you see we got our window?
Hi.
Yay. Okay. Inferential statistics. 2 sample. I'll have to type it in again and watch. I am going to have to do something for a second, because someone doesn't know that they are unmuted. There we go. Oh, I'm frightened to do this. Are you looking at salt right now? No. Oh.
You're not sharing a screen.
Yeah, right. I'm not. I'm trying to. I started today by having
there.
Can you see it now?
Yeah.
Yeah. I started today by my mic not working. And it looks like today's just today. It's probably the Russians. That's what I'm blaming. They've decided to pick on me.
That's funny.
Right, the sample mean.
I want to joke about that.
Okay, the sample mean. Back to the beginning. These are the cold people. They got 7. It lasted for 3. Sorry, standard deviation was 3, and the sample size for them was 29. It is nowhere near as hard as I'm making it. It's just technology and annoying me. So the people who got the lozenge are 4.5 days. 1.5 was the standard deviation, and that there were 21. So confidence interval, let's say it's 95. We're not going to tick on that assumed equivariance. You will only do that if they mention pooled data, and will generate results. So the difference between them is 2.5. If you wanted a 95% confidence interval, it's 1 point that to 3 point that. Do you see the weird number for the degrees of freedom? Right, our sample was 21 and 29. If you add them together, it's 50, isn't it? The reason it's 43.42 is they're probably using that weird formula. Thankfully, we don't need to worry about it. Anything else you want is either here or down here. These are the individual days. So if you take the ones that had the cold, their standard error is that. And if you take the ones who got the placebo, their standard error is that. So all I need to do now is figure out No, you can't be doing this. There we go. Right, there's the Mini 2.5. Can you remember that one we saw a moment ago? I'm assuming that 0.484 is going to be in I'm not doing it. Can you trust me that the thing was 0.484 before I lost my window again? I don't know what the heck's going on today. Here's a little picture of what that might look like. And there's another one at the bottom. So sorry for all those weird stuff. I'm going to try a different strategy for the next one. So this one is question 11. The data given was college students, and we asked them what the fastest they were driven. And I'm going to hit use salt. And I am going to put this as two windows next to each other. So with a bit of luck, I won't lose one of my windows and can't get it back. So in this particular story, let's see what we've been asked to do. The data is given by college students in response to question, what is the fastest you've ever driven your car? And the variable fastest speed contained in response. So the difference we're looking for is the difference between men and women going first. Okay, so we want 6 and fastest speed. So I'm just going through here and taking the two variables, there's 6 and the fastest speed. And we're going to create confidence interval for it. So the two sample is going to be, that's done. And evidently it's already picked up all the numbers. So I should just do confidence interval and generate results. Not convinced by that, but that is over with. I'll have another look once I've figured out why my software is losing my windows. And when we see you tomorrow, we're not finished by the way, but when I see you tomorrow, I'll probably have this thing figured out. I'm not convinced that that last answer was correct, but I'm not sure if I'm just having a bad day or what. So let's move on to our last section. We are looking at what's called hypothesis tests. Hold on for a second. I've lost another window. What the heck is going on today? Is anybody else having problems with their software, or is it just me having a bad day? No, it's me having a bad day.
Yeah, I think it's just you.
No, somebody's got it in for me. That's what it is. Okay. The chapter that we're doing, or at least getting the intro for, is going to be chapter 12. And tomorrow when I get you, as I said, I'm going to figure out what's going wrong with salt so that when I show you what it should be doing, actually starts working. Essentially, a hypothesis test is how we prove things in statistics. Any statement. And in the jargon, we call that hypothesis. So how do you prove any statement or hypothesis in statistics? It is a very formal proof. What you basically do is that you give two options. Right, so there are going to be two options. The first option is called the null hypothesis. A null hypothesis is basically that nothing has changed. Sometimes called the status quo. So to give you an example of what that might look like. Suppose we were interested in the following story. "20 years ago, the percentage of people adults who smoked was 37%. And we believe it has now changed. In particular, we believe it's got smaller. Right? So how do we prove to the scientific world that this statement, this hypothesis, is in fact correct? Right, well, we have two options. The first one is called the null hypothesis. That has nothing changed. And we write it down like this. H naught, two little dots, P equals 0.37. Second option is called the alternate hypothesis. In this case, it's written like this. HA, two little dots, and we believe that the percentage of people who smoke today is less than 0.37. And when you put these two together, that's what we call a hypothesis test. We are going to test the statement. Is there evidence to prove that things have actually got smaller? So far, so good. Think of it like a court case. And we're bringing it to the court and we're going to try and prove that this guy is true, right? So how do we go about that? Well, what we typically do is we collect data to try and prove the alternate hypothesis. So you go out there and you get a sample. And let's say your sample was 200 people. And that your sample proportion out of your 200 people was 70. Yeah, let's go ahead, I'll try it. Don't know where it's going to be. Was 70 out of 200, which is 0.35. Now we got a problem here. That is definitely less than 37. And some people would say, oh, well, that's it. I've proved it. My sample was a smaller percentage who smoked than a way back 20 years ago. So that proves that fewer people smoke today than did in the past. Why is that not good evidence? Why can't I just say that's it and leave?
Margin of error, it might be 37, despite it being 35.
Yeah, you could easily have another sample that was 38, couldn't you? Isn't there always variation in samples? And we have to figure a way of deciding how unusual this would be, right, as a sample, if this statement was true. So I'll say it again. We try and show or prove how unusual, right, how rare this would be if that's true, right? And if this is so small, right, the chance of this happening if this was true is tiny, then we have got the evidence that we looked. So how do we decide how unusual something is? Well, we factor in a new thing. All hypothesis tests have a value associated with them called the significance level. And it's called alpha. And this is an example of it. So if you wanted to say that out loud, you would say alpha, equals 0.05. If this number is unusual, that means the probability of it happening is small. Alpha is how small it needs to be before we're going to convict them. Analogy: can you imagine that you were doing a murder trial and there was a guy put up in court and you were going to charge him with murder? If you think about it, don't you want the, how would we do that? You know that someone who is convicted of murder doesn't actually guarantee that every single time that happens, the person really did do the murder. Would you agree? There is always going to be a small percentage that you've just met the unluckiest guy in the world, right? That the circumstances and the evidence that you've got were good evidence, he still didn't do the murder, right? And so when you do a crime case, or if you're convicting someone, don't you want this to be tiny? You want to say, look, if I say you're guilty, I know the chances I got that wrong are really small. So I want you to think of that number as the probability that you got it wrong. What does that mean? It means that you say, oh yeah, we've proved something, when you haven't. So that means you say you have proved the alternate when it was in fact true. So that would be a bit like convicting someone that was innocent. Now, you can't make it 100%. You can't make the chances of getting yourself wrong as 0. Would you agree that's just impractical, right? But don't you want it to be very, very, very small if it was a court case? Now, if I was doing, well, I don't know, I think people like Pepsi more now than they did in the past. Would you'd be okay with being wrong 5% of the time, right? Because, big deal. People are smoking less than they used to. I could live with 5%. The standard significance levels are, in fact, 0.1, 0.5, and 0.01. Those are the normal significance levels, right? The chances that you are willing to be wrong. So what we now have to do to kind of finish this puzzle is we now have to find what's called the p-value. And the p-value is actually a probability, and it's a probability that you got the sample you have given that H naught, that's in this case P equals 0.37. So we are going to find what's the chance that you could get a sample of 0.35 if the population number was that. So let's put some of the pieces that we've got right now. For this story about smoking, I have the null hypothesis is nothing has changed. It's still 37. And the alternate is that it's got smaller. I have a significance level. What do you want? 0.5, 0.1, 0.05. What do you want to choose for this story that we're doing?
0.05.
Okay. Do you know another way of looking at that? I'm 95% sure I got it right, and I'm 5% sure I got it wrong, right? So it's two different ways of seeing it. So you've set that up. What you now do, so that would be essentially our step one, and that is setting up the hypothesis. Step two is find p hat, standard error of p hat, and a z-score. So we are going to find these fellas. In my story, we got p hat was 0.35. The standard error, this is where people tend to make the mistake. There are two numbers floating about here for who we should be doing here, right? What do I mean by the two numbers? It could be 0.37 and it could be 0.35, right? You always choose this number here. And it even has a name, it's called P0. So it's P0, one takeaway P0 over N. So your standard error is not going to be from the sample, it's going to be from whatever number is used in the null hypothesis. Because what we're doing is we're saying, look, this is meant to be true. What's the chance that this could happen? So we're going to use this number, assuming that it's more accurate because of it. So it's going to be 0.37 times 0.63, all divided by 200. So it's going to be the square root of 0.37 times 0.63 divided by 200. Close it down, and we got it. And the number I've got here for the standard error is 0.034. So I found that guy, check. I found that guy, check. I now have to find z-score. Z-score will be found by using this formula. It's going to be the sample, take away this guy, divided by the standard error. Our sample is 0.35. This guy is 0.37. And it's going to be divided by 0.034. So that's going to be a negative number. Let's find out what that number is. 0.35 take away 0.37, all divided by 0.034. And the answer I get is negative 0.59. And that's our Z-score. Now this Z-score is the same Z-score that we found for lots of things over the last 8 weeks. Does that look like an exceptionally unusual Z-score? What kind of Zs are really unusual? Aren't they things bigger than 3 and less than -3? That's unusual. 2, yeah, 2 is pretty rare. -2, pretty rare, right? 1 point something? Nah. 0 point something? Definitely not. So I'm already suspicious that we haven't proved, right? We haven't managed to prove it. But the process continues. My gut feeling is that we're not going to be able to show that this is strong enough evidence. So here is step 3. You're going to find this magic guy called the p-value. And in this case, the p-value is the probability that you get a Z-score less than negative 0.59. So that's basically how unusual is it to get that kind of Z-score. That's essentially what this is calculating. So if you can imagine my little normal distribution with 0, we've got a guy here roughly 0.59, and we are trying to find out that. Now you might say, well, why is it not bigger than that? You know, why do we go this way? You see this fellow over here, the alternate hypothesis? Aren't we trying to prove that it's less than something? So we have to look at Z-scores less than something. And that something is your p-value. Right? Now this is done, here we go. This is going to be done using salt, but I'm not going to show you salt because it's a pain in the butt right now. I'm just going to do it, and if it works, I'll show you. Okay. Okay, go figure, it's worked. So click over to salt, and we are going to find out what's the probability of getting a Z-score less than negative 0.59. So you click on distribution, normal distribution, that's where we're going. That's 0, that's 1, leave it alone. We want to find the chances that you get less than negative 0.59. And the answer is that guy there. Would you agree that's a big chunk of change here? That's not that unusual, right? You could easily get that. I'm writing this number down, it's 0.2776. Let's just continue this process. So, quick recap. That's what it was 20 years ago, 37%. We think it's going down. So our alternatives, we're trying to prove that it's less than that. The chances that we're willing to be wrong is only 5%. That's what this fella is. We find p hat, sample. We find the standard error using this number. We get Z-score using this formula. We then find the p-value, which is going to be the probability that we get a Z-score less than this guy, which I just did, and ends up being that. That's about 27.5%. 0.76%. Would you agree that that's likely to happen about a quarter of the time? Right? That's not good news for evidence here. So our final step, step 4. Our conclusion. And this is how, again, it's a bit lawyerish, but this is how it's done. You do a test and you say, is the p-value that we got, is it less than the significance level? If the answer to that is yes, then you have found enough evidence to prove the alternate hypothesis, the one you were hoping to prove, is true. Is the p-value, I'll give that the equals, is it greater than alpha? That can happen as well, right? If the answer to this is yes, it is, then you have not found enough evidence. Now, it doesn't mean that that is true. All that means is that we haven't found enough evidence. Analogy. Can you think of the court case? If someone was on trial for murder, the verdict you get is guilty or not guilty, correct? Now, guilty is basically this one, right? You're guilty, we've proved it. The alternate sentence or decision isn't it not guilty? Does not guilty mean that the guy's innocent? Could it also mean that he done the crime, there just wasn't enough evidence to prove that he done the crime? And that's actually a slightly different interpretation of that. That's what this means. We don't know if that's true. There's just not enough evidence to prove that it's true. On the other hand, if this happens, we say, you're guilty. We've got enough evidence to put you in jail. Are we sure we put you in jail? Well, we're kind of 5% chance of getting it wrong, but we're willing to live with 5% chance of getting it wrong because nothing's perfect in the world. Well, let's look at our test. Is our p-value, which was, I'll write it down, is our p-value less than 0.05? Well, is 0.2776 less than 0.05? Nope. Isn't 0.2776 actually greater than 0.05? Right. This is too big. What's our conclusion in this story? It's going to be not enough evidence. When they do criminal trials, very often they bring in scientists to try and prove things, right? Like, this footprint could only have been made by this foot, right? And things like that. They're basically employing this type of process. Now, there are certain things where this p-value is tiny. I'll give an example. If we find your DNA on the dead body, and you said, I've never seen that person in my life before, do you know the chances of someone else having your DNA is actually negligible? Would you agree that nobody in the universe has got your DNA except your DNA? That would be a p-value of like 0.4 million zeros and a one, right? On the other hand, if you find the blood group and it's a B positive. Would you agree there's lots of people in the world with B positive blood? Not just you. So you wouldn't, that p-value, couldn't that p-value be 27% of the population has got that blood? Why are you convicting me of the crime, right? I'm just trying to give you the analogy. You don't want this guy here to be big, because if he's big, it means that what you got in your sample could just have happened by randomness. There's nothing to see here. So you want a p-value to be small. So when you look at scientific papers or medical results and they try and say, we have proved X, Y, Z, whatever it is, there will be a p-value associated with that test. And you can look at that p-value. And if it's nothing 0.00007, won't you bet your house on it being true? But if it's nothing 0.09, aren't you going to say, oh, that's a 9% chance of them just getting it wrong? Do I really want to bet my house on that kind of evidence?